In this recording, we talk about electrical potential. Electrical potential is somewhat of a new concept to us. There is no equivalent that we have used in terms of gravity. The first distinction that we need to worry about, it's not electrical potential energy. It is what we call electrical potential. The main difference is for electrical potential energy, we need two charges. For electrical potential, we need just one charge. Very much like for an electrical force, we need two charges. But for an electrical field, it's enough to have a charge. We have an electrical field due to one charge. Here it's the same thing. To have an electrical potential energy, we need two charges. And remember, the expression for electrical potential energy is K Q1 Q2 over R, where R is the separation of the charges. Now, for electrical potential, the symbol we use for it is V, and it is just KQ over R. It is essentially an electrical potential energy per unit charge. It's UE divided by one of the charges. That's what we define as electrical potential. We sometimes also call it as voltage, but the more correct term is electrical potential. So we define electrical potential as V equal to KQ over R. It's the electrical potential due to any charge. Any charge is going to have an electrical potential associated with it. Very far away from that charge, the electrical potential is going to be zero. For R very large, V becomes equal to zero. R, the distance away from the charge. So if this is where my Q1 is, the electrical potential a distance R away is going to be given by V, K, Q over R. If it is Q1, it's V Q1, K Q1 over R. Now, the sign of V depends on the sign of the charge. If the charge is negative, V is negative. If the charge is positive, V is always positive. It is a scalar. Now, think about gravity. Think about if this is the ground and we place a mass here. We can say it has a gravitational potential energy mgh. Now, what if we don't have the mass? We can say gh is the gravitational potential at the height h. So gravitational potential, that's something we didn't talk about. It's not gravitational potential energy. It's gravitational potential. There is no energy there. There's nothing. But if we place a mass m in there, then the gravitational potential energy would be m times that gravitational potential, m times gh. So gh is essentially the equivalent of our voltage, kq1 over r. So there is no electrical potential energy. There is only electrical potential, but once we place another charge Q2 here at that location, then we have an electrical potential energy that's going to be V times Q2, which comes out to be equal to KQ1 Q2 over R. The unit for electrical potential is joules, the unit for energy, divided by the unit of one charge, which is a coulomb. Joules divided by coulombs, we call that volts. That unit, you are familiar with it in terms of outlets. For example, we have 120 volt outlets or 220 volt outlets at our homes. Batteries, 9 volt batteries, 1.5 volt batteries. That's the same unit that we use for electrical potential. we'll see later on, usually when we deal with batteries and outlets, we don't worry about electrical potential, we worry about changes in electrical potential. Like for gravitational potential energy, we worry about changes in gravitational potential energy, not gravitational potential energy. Okay? Now, so again, in summary, the electrical potential is a new definition. The expression for it is kq over r, where r the distance away from the charge. It is a scalar, that is positive for positive charges and negative for negative charges. It is it becomes zero very far away from that charge at infinity. It is not energy, but when we have an electrical potential, if we place a charge in that electrical potential, then we have electrical potential energy, and the unit is volts. Now, in terms of gravity, I said think of it as height times g, because g times h, if we multiply it by the mass, we get the gravitational potential energy. Like when we multiply the voltage by the charge, we get electrical potential energy. Now, to get a better understanding of what I mean when I say think about height, I have here a topographical map of, this map is from the USGS. Now, it seems it's not really up to date. They list Kennesaw State University as Kennesaw State College. But notice here, what do they do in a topographical map? You see these lines here? For example, this line here is 1020. I really didn't investigate it more carefully. I would think that's 1020 feet above sea level. It can be meters, but I think it's feet above sea level. So here it is telling us all these points are at that height above sea level. Now 1040, that's a little higher. Here 1080, that's a little higher. 1000, a little lower. So these lines are tracing for us levels that are at the same gravitational potential. Now if I place a mass here, it's going to have more gravitational potential energy than if I place it here. It's going to have an amount gravitational potential energy that's going to be g times 20 feet times the mass. That's the difference in gravitational potential energy that it's going to have. The mass, whatever mass I'm going to use, times g times the difference in height, 20 feet or 20 meters, whatever units they are using here. I believe it's feet. It will not be very plausible if it is meters. Okay, but we see like we have some high points here. 1080. It is not showing us much here, but people who are very versed in topography, they can read it more carefully. We have 1100 here. We should have some height here near where the dorm is, but I have no idea. Okay, now that's this illustrates for us gravitational potential. Now we have the same thing for electrical potential. Okay, what I'm going to do here, I have the graphics, but I'm going to go to the simulation. I have it running in the side here, I believe. Okay. Now, so I have a reservoir of charges, and I can pull in any charge. For example, I'm going to take a positive charge. Now, you notice here, I have an electrical potential reader, and it's going to read for me the electrical potential in volts at any location. The closer I get to the charge, the larger the electrical potential. The further away from the charge, the smaller it gets. And now this one allows me to plot the equivalent of topographical maps. For example, here it is drawn for me a circle that has an equal value of potential, which is going to be 15.9 volts. Anywhere around there, if I go, I'm going to read 15.9 volts. Okay, I'm not doing it precisely here, but if I go there, I should be able to read 15.9 volts at any point. Now, that's an equipotential line. This is, I can put another one here. So these are essentially the topographical maps or the equipotential maps due to this charge. Now let me clear this. What if I have a negative charge instead? See, the electrical potentials in this case are negative. It's the same idea. They increase as I get close to the charge. They increase in the negative sign, but then they get closer to zero as I move further away. And again, I can plot equipotential lines. Lines where the potential is the same. And they are circles here because of symmetry. In 3 dimensions, they would be spheres. Okay, let's clear this. Let me show you something first before I move to the next part. We can actually have a more sophisticated drawing. In here, we see it as a continuous gradient in changing the colors of the electrical potential values. The dimmer the color gets, the lower my potential value is. Okay, now let's have 2 charges, a positive charge and a negative charge. Now in this case, the places where the electrical potential is going to be calculated is going to be affected by both charges. I'm going to have an electrical potential due to the positive charge and an electrical potential due to the negative charge. They are going to add up. One of them is going to be positive, one of them is going to be negative. So in some places they are going to add up to 0. In some places the potential due to the negative charge is going to be larger than the potential due to the positive charge, and we get a negative electrical potential. In some places we are going to get the opposite. And let's look here at the so in this place, for example, it looks like I have 0 potential. In this place I'm going to have negative potential. In this place I'm going to have positive potential. And I can continuously draw equipotential lines. We'll leave this graph like this, we'll go back to it later, but let's go back to the simulation. So we can get lines that look somewhat like this. These are lines where the voltage or the electrical potential is constant. And the configuration, of course, depends on the charges we have. In this particular case, I have a large and a small positive charge. In this case, I have a negative and an equally another negative charge of equal size. In this case, I have a large negative charge and a positive charge, and these are the equipotential charges due to them, so you see different configurations. Okay, now here we discussed the electrical fields. The equipotential lines, or the lines where we have the same potential, are still drawn, but the electrical field, remember, is going to point away from a positive charge, like you see it here, pointing away from a positive charge, and towards a negative charge. Okay. Now if we go back to the simulation we were just playing, so if we tell it to show the electrical field, look at the way the electrical field is. Towards the negative charge and away from the positive charge. We can also put electrical field sensors. So here it is pointing towards the negative charge, and here still pointing towards the negative charge. You notice we have an electrical potential of 0, but the electrical field is not 0. And it is pointing away from the positive charge. But one thing that you notice, the electrical field is going to point downhill from the electrical potential. Remember, this is the largest value of electrical potential. Now if I go here, it is a smaller electrical potential, and here it's a smaller electrical potential. So the electrical field is always pointing downhill. Now if I go here, it is also going from 0, then it's downhill, it's decreasing. In other words, if we take a positive charge, it's going to look like it's rolling downhill in the same direction as the electrical field lines that are drawn here. If we have a negative charge, it's going to roll downhill towards the negative charge, of course.